All right, activation energy and yay, temperature dependence of rate constants. All right, here's the deal. With very few exceptions, reaction rates increase with increasing temperature. If you raise the temperature, the rate increases. And as a nice general rule of thumb, for every 10 degrees Celsius you raise the temperature, the reaction rate doubles. Which means for every 10 degrees Celsius you lower the temperature, the reaction rate is cut in half. And this is why we refrigerate and freeze food. Because if you have your lunch meat sitting out on the counter on a warm day, it's going to spoil pretty quickly. A warm day, say it's 30 degrees Celsius, that's awful warm. Say it's like 27 degrees Celsius or so. Then, whoa, that meat is going to spoil at those temperatures. But you put it in a refrigerator, and your refrigerator is normally kept pretty darn cold. It's normally kept like usually about like 36 degrees Fahrenheit. That's usually, that's in the range of like 2-3 degrees Celsius. And so what that means is when food spoils, part of the spoiling process is oxygen getting to it. It's a chemical reaction. Well, you have decreased the speed of the spoiling by a factor of 2. When you dropped from, say, 27 degrees Celsius to 17 degrees Celsius, that 10 degrees Celsius difference means the food's going to spoil in half the time, or is going to take twice the time to spoil. But note, if you drop it another 10 degrees, it's going to take 4 times the length to spoil. So cooling things down slows down the reaction quite a bit and allows your food to stay fresher longer. And if you freeze it, boy, then it's really cold, and as an added bonus, the water freezes, and so you have solids, and solids tend not to react very well. But this is the deal. And this is just a nice thing, the general rule of thumb. For every 10 degrees you increase the temperature, the rate of the reaction is going to roughly double. Why is that, though? Well, here's the deal. We must look at the collision theory of chemical kinetics. And this isn't too hard, not too bad. All right, it basically says this. Molecules can only react if they hit each other. They need to slam into each other. Two reactants can't be on opposite sides of the jar and react with each other. They have to be very, very close together. It turns out they have to run into each other. Because the first thing that usually needs to happen is you need to break some bonds, and breaking bond requires some energy, and you get that energy out of the collision of those molecules. Two things smacking together provide a lot of energy. That kinetic energy of the motion of two molecules when they hit can be transferred into vibrational energy of bonds so much that it breaks bonds. And so the faster a reaction means we need two things. We need the molecules to hit each other more often, and we need them to hit each other with a greater force. The higher the force of the hit, then the more energy of the collision, the more energy that can go into breaking bonds. All right, and also the more molecules that are there, the higher the chance they have to hit each other. So the higher the concentration is, the more collisions you get, the faster the rate of reaction. However, there is a bit of an issue. If you look at a molecule in the gas phase, 1 atmosphere, 298 Kelvin, room temperature, that's 25 degrees Celsius, you have roughly 1 times 10 to the 27th binary collisions per second, meaning two molecules smack into each other. Every second, two molecules will smack into each other. You'll find two molecules smacking into each other 1 times 10 to the 27th times. That's a huge number. And that's in only 1 milliliter of volume. If you're in the liquid phase, the molecules are even closer together. There's even more binary collisions. If every single time a reactant hit another reactant, the reaction actually occurred, all reactions would be done almost instantaneously. All reactions would be done in less than 1 times 10 to the minus 27th of a second. And that's not the case. Most reactions take much longer than this. So there must be some other factors that mean that not all of our collisions are going to lead to products. And the factors are, the two main factors, the first one is going to be the kinetic energy. We know the faster something moves, the more kinetic energy it has. As I had said before, when molecules collide, the kinetic energy is converted to vibrational energy that are, if large enough, they can break chemical bonds, and that's the first step. Note, if two molecules smack into each other but the kinetic energy is too small, then you're not going to break any bonds, and the two molecules will just bounce off of each other. So it turns out there is a minimum energy of the collision. When the two molecules smack into each other, they must have a certain amount of energy, below which, if they don't have that, at least this level of energy, then no reaction occur. If the energy is above this level, the reaction can occur. And that energy level that the collision must have is called the activation energy, given the symbol E sub A. All right. And when the collision has enough energy, you will form an activated complex, and this occurs at the transition state, which is going to be at the top of, down here. All right. Here's our activation energy. When you get these reactions, the collisions have enough force to make an activated complex, which occurs at the transition state at the top of the diagrams we are about to draw. So let's look at this graphically, because pictures are very nice. If you have the reaction A plus B goes to C plus D, general reaction. If we look at the potential energy, all the energy stored in the bonds on this axis, and axis is called just reaction progress, how the reaction is proceeding. At the beginning, we just have the two reactants, A and B here. But if A slams into B and there's enough energy to overcome this activation energy, that means you've added enough energy to break the bonds. We get this transition state at the top of the hill. This is when halfway between A and B, and we will discuss, especially when we get to organic chemistry, what the transition state looks like. But it's halfway through the reaction. It could be the bonds are breaking, because truthfully that's the main thing that happens as you add energy, is bonds are breaking. And then after the bonds are broken, you start making the bonds, and that's going to release energy when you're making the bonds. But you have to have enough energy to break the bonds to overcome various interactions, and that is the activation energy. And when you're halfway through and you've overcome most of those interactions, we're at the transition state. Note, in this reaction here, we have the energy of A plus B. A and B separately, they did the reaction, rearranged themselves. A smacked into B with enough energy, overcame this energy barrier. And then when the bonds start forming to make products C and D, it turns out the potential energy of C and D is lower than the potential energy of A and B. Recall that molecules store energy, that potential stored energy is stored in their bonds, which means C and D have less potential energy. They are more stable than A and B. The question is, where did that energy go? We had to add energy to this reaction to get it over this energy hump, the transition state, over this activation energy hump. So we had to add this much energy, but we got back all that energy we added, and then we got back more energy. And that energy that got given off, that extra energy that got given off, because C and D are more stable than A and B, got given off as heat. And so our reaction is exothermic, because the energy of the products are less than the energy of the reactants. The products are more stable than the reactants. The products are at lower energy. They gave off that excess energy in the term of heat. However, some reactions, when you react A and B, you give it the proper activation energy, give enough energy to overcome this barrier here through the transition state, but the energy of C and D here is higher than the energy of A and B. So it took some energy. You had to add energy to go over this hump. You had that activation energy, but you didn't get all the energy that you added back. You had to add this much energy. You only got back this much energy. Therefore, C and D are less stable than A and B, and this reaction takes in energy, takes in heat. This is endothermic reaction. And you'd know that if while the reaction was going, it got cold. It had to take in heat from its environment. All right. Now, sometimes these hills look a little bit different. Occasionally, we're gonna find we have multiple step reactions where A plus B will go to C and D, but then C and D might just turn around and react with each other to form two new products, E and F. When that happens, you look at the potential energy of your two reactants. You have to go over that activation energy hump, and then you get this minimum here in this curve. We call that an intermediate. And then the intermediate will react, takes some activation energy for those two to react, and then we get our final products down here. All right. So question, why do some molecules have enough kinetic energy while others don't? Why do some collisions result in bonds breaking and others do not? Well, let's look at a situation here. Let's just say we've got water sitting on a table and it's evaporating. Water in the liquid phase is going to water in the gas phase. Well, here's the problem. We know to get from water to go from the liquid phase to the gas phase, don't we have to raise water to its boiling point? Isn't the boiling point of water 100 degrees Celsius? Don't you have to add so much energy to water to get those water molecules moving so fast, give them enough energy to break the hydrogen bonding intermolecular forces? And the energy required is proportional to the temperature of 100 degrees Celsius? Yeah, that is true. But the water on the table is still going to evaporate even though the temperature of the water stays room temperature, roughly 25 degrees Celsius. And the reason it happens can be shown in this graph. Let's look at this T1 graph where we're looking at this curve right here. When we look at the speed of the water molecules, which correlates to the kinetic energy of those water molecules, and we remember the kinetic energy is measured via temperature, we look at the speed of those molecules, it turns out most of the molecules do not have enough speed to evaporate. This line right here, this point right here tells us how much energy the molecule must have before it can leave the liquid phase and go into the gas phase. And what we find is that if we look at an individual water molecule, we can measure its speed, thus its kinetic energy, which is related to temperature. And we find some molecules are moving really slow at very low speeds. Some molecules are moving much quicker, and some are moving very, very quickly, have high speeds, high kinetic energy. So any one individual water molecule might be going slow, might be going medium fast, might be going real fast. But when we look, here is the average speed, which corresponds to the average temperature of 25 degrees Celsius. So on average, the molecules are moving much too slowly to go into the gas phase. Much too slowly, they do not have enough kinetic energy to break the hydrogen bonding interaction. However, some of these molecules do. Right down in here, these molecules right here do have enough energy. This small fraction of molecules, of water molecules, do have enough energy to escape into the atmosphere, to break the hydrogen bonds. So they do. They do leave. Now, what happens to the rate of evaporation if you heat up the water? Well, if you heat up the water, the average temperature goes up. So now, if the average temperature is going up, the speed of the molecules, the average speed of the molecules is faster. And when we look at this curve now, if the average speed is faster, now a whole lot more molecules have enough energy to overcome the hydrogen bonding interactions, and so they leave. So if you heat it up, the molecules go into vapor phase much faster because many, many more of them a larger percentage of the molecules do have enough energy to break the hydrogen bonding. But if you're not heating it up, this is shows another interesting phenomenon that you're probably aware of. If you had just water sitting on the desk and some of it evaporated, note which molecules evaporated. The highest energy molecules, the ones that are going fastest, the ones that have the highest kinetic energy, one could consider them the warmest. The hottest molecules are the ones that leave. So if these molecules leave, what happens to the average temperature? What's going to happen to the average temperature if the hottest, fastest molecules leave? Answer, the temperature is going to go down. Now the temperature will go down, but it'll spread out again, and there will still be some molecules that through collisions will gain enough energy that they can leave too. And the temperature will go down a little more, which is why when water evaporates, since the hottest molecules are the ones that leave, water gets colder when it evaporates. This is why you sweat. As the water molecules leave your skin, it's the hottest molecules that are leaving. The ones that remain are cooler, and so that cools you down. Okay. Now, that was water, but these diagrams can be looked at any reaction. If you had molecule A colliding with molecule B, they are only going to result in a reaction if they have enough kinetic energy. Some of the reaction A and B collisions are going to result in the reaction, but a lot of them will not. The higher the activation energy means the higher this barrier, or the further to the right the energy is needed to be, the more kinetic energy is needed. The higher the activation energy, the fewer molecules that have enough energy to actually do the reaction, the slower the reaction is going to go. So it is this activation energy, this hump in this diagram, that must be overcome. The higher this activation energy is, the more energy that has to be added, which means at any given time, the fewer molecules have enough energy to do the reaction, the slower the reaction is going to be. All right. And you're saying, that's cool, but what about the math? Ah, sweet. Now it's time for some math. And we will end this video here and start up with the math next time.